So, in the last class we have studied about elliptic curves and their definitions. So, in today's class we shall concentrate on how to apply elliptic curves to cryptographic operations. So, in today's class we shall essentially cover these areas like what is the relation between elliptic curves and cryptography, discuss about an Elgamal type of encryption algorithm in context to elliptic curves. So, the other important thing that is needed is how essentially do we take a message and encode that into the elliptic curve. So, we will see a very simple algorithm to do so, and also the corresponding decoding, that means given the corresponding point how do we get back the message. Then we shall discuss about the Diffie-Hellman key exchange in context to elliptic curves, and then we shall address like why do we at all use elliptic curves, because we have studied RSA and public key ciphers which are based on discrete logarithm problems. So, what is the purpose of elliptic curves and what is the underlying hard problem behind elliptic curves. So, we shall just discuss certain issues in these contexts. So, first of all, to start with public key ciphers, as we have seen, there are two important requirements in public key ciphers. One is secrecy and other one is authentication of information. So, as we know that in any public key crypto system, these are provided by a pair of keys, right. So, if you know that if you want to apply your public key cipher for giving you secrecy, then also you use a pair of public key and private keys, and similarly if you want to use it for authentication, you use another pair of public key and private keys. The only difference when you are using it in context to security and when you are using it in context to authentication is that how do you use, which key do you use for what reasons. Like for example, when you are interested in the or motivated in the security of the secrecy of the information, then you use the public key for encrypting, right. The sender uses the public key, but the receiver decrypts it using the private key. Similarly, when you are using it for authentication, you can use the same public key, but you have to use it in the other way. That is, if you want authentication, then you have to use the private key for sending the data and use the public key for verifying, right. So, similar to that we can also use, so that is basically shown in this diagram, that there is a source A and there is a destination B, and the message source wants to send X, which is a message, and it wants to send it to the destination, ensuring that both secrecy of the information and the authentication of the information is maintained. So, for that source A chooses a pair of messages, pair of keys, and for encryption algorithm, so there are two stages of the algorithm. One is the encryption algorithm, one is the encryption, the public key encryption has been used for secrecy, the other one is used for authentication. Okay. So, when you are using it for encryption, then you are using the public, because you have to encrypt the data. So, you essentially choose the public key and you encrypt the data and send it to the receiver, but for authentication you do just the opposite, that is you essentially choose the the private key for sending, and similarly you want to verify. So, in order to verify you use the corresponding private key. So, therefore, for if you want to send it for authentication, then you see that you have essentially chosen the public key for performing your authentication, right. So, the private key for performing or signing the data, and for verifying you use the corresponding public key. But if you want to use it for secrecy of the information, then you use just the keys, but in same keys or similar pair of keys, but in the other way. That is, what you do is that you choose the public key for performing your encryption operation, and you decrypt the corresponding cipher text by using the corresponding private key, right, because anybody should not be able to decrypt. So, therefore, the secrecy of the data is ensured, because you know that the secret key is only that is assumption, right, that is the secret key only B has the corresponding secret key. So, therefore, or the private key, and therefore, it can only decrypt. And similarly, the authentication is ensured, because the verification, if the verification is successful, it shows that and based on the assumption that only A has the corresponding private key. So, he knows that this particular message digest can be only generated by the source A. That is, since the apart from source A, nobody has the corresponding private key, therefore, only A can sign this message, right. So, therefore, the authentication is also ensured in this fashion. So, this is a very customary operation of how you basically. So, there are two important parts, one is the encryption and the other one is the authentication. So, what we understand from here is that what we have studied previously is that you can use any encryption or any public key encryption algorithm and you can actually achieve these goals of encryption as well as authentication. Okay. So, for encryption you know that there is a public key, that is a public key ring. So, if you want to communicate with anybody, for example, if you want to communicate with Alice, then from the public key ring you choose the corresponding key, that is for the corresponding public key for Alice, and you generate the ciphertext, and the receiver, since it has the corresponding private key, decrypts the message and obtains the corresponding plain text. When you are doing the authentication, then what basically you are generating the signature. So, you take an input and you sign it by your own private key and you send it, and you see, and if this receiver is expecting the message from Bob, then it chooses the corresponding public key from the public key ring and decrypts it and obtains a plain text message. So, you see that both these essentially uses the same public key cryptography ring, but the point to be noted here is that when you are using it for encryption and when you are using it for authentication, the public key ring is in the first case present in the receiver, in the sender's part, and in the second case it is present in the receiver's part. Okay. So, that is a small thing which is to be kept in mind. Now, there are various arguments about whether you should do the encryption first or whether you should do the authentication first. Okay. So, so that essentially is a matter of we can argue on that, but this is the basic way how you can actually choose the public key, and you can actually perform either if you want to use it for the secrecy or you want to use it for the authentication of the information. So, therefore, what is elliptic curves? We have studied that elliptic curves is essentially, elliptic curves is basically a certain set of curves that is essentially what we have studied in the last class. So, now the question is, what is elliptic curve cryptography? So, elliptic curve cryptography is nothing but a public key crypto system, just like we have studied RSA, we have studied LGAML. So, it also has a public and a private key, okay, and the public key is used either for encryption or the signature verification, and the private key is used for decryption or for signature generation. So, elliptic curves are used as an extension to other current crypto systems. So, therefore, you can also have elliptic curve defilement key exchange, you can have elliptic curve digital signature algorithms. So, wherever you have seen the previous applications of public key ciphers, you can have similar applications here also, but these are actually based on certain curves which are known as elliptic curves. So, there are certain cubic curves which we have studied in the last class. Okay. So, now we shall study that how do we apply these elliptic curves to generate a public key cipher. So, the central part of any crypto system which involves elliptic curves is the elliptic group. Okay. So, we have studied that if you want to generate elliptic groups, then for that in order to do that we actually define certain operations. So, the operations means those we take 2 points on the elliptic curve and we define what is meant by addition on these 2 points, right. So, we define what is meant by point addition and what is meant by point doubling. Okay. So, all public key crypto systems have some underlying mathematical operations, like if you want to, for example, choose RSA, then you have exponentiation, right. You know that you will basically do a modular exponentiation, and all public key ciphers essentially relies upon certain things which are assumed to be one way functions, that is some functions which are easy to compute, which are difficult to invert. Okay. So, in context to RSA, we have seen that the hard problem or the one way problem was essentially what? Essentially was the factorization problem. That is, if I can take two, if there is a large product or if there is a large composite number which can be factored into two large prime numbers, then it was believed that it is difficult to factorize these moduli, right. So, that was the assumption on which the RSA's security was relying on. So, when we studied about the LGAML crypto systems, which was based upon the finite field, for example, FP or any other finite field for that matter, then it was based on the something which is called as a discrete log problem. So, it was believed that it is easy to compute given a public moduli G and given a secret modulo X, right. It is easy to compute G power of X modulo P, but from G power of X modulo P, it is actually believed to be difficult to compute the value of the exponent X. That was the assumption on which the LGAML crypto system was based on. So, similarly here also in elliptic curve cryptography, we also have something which is then similar or analogous to the discrete log problem, and which is called as the elliptic curve discrete log problem. So, this essentially is again relies on how do we do the point addition and how do we do the point doubling. Okay. So, the underlying mathematical operation on which these public crypto systems based on elliptic curves are based on are actually something which is called as point multiplication. So, what we do is that we take a elliptic curve and say for example, consider any elliptic curve for that matter. Okay, suppose this is one elliptic curve. So, what we do is that we take a point P on this curve and we take another point Q on this point and we do a point addition. So, that is what we have studied in the last class, right. So, therefore, this essentially intersects the curve at a third point and the corresponding reflection of that point is a sum P plus Q. Okay. So, this is known as the sum P plus Q. Similarly, if there is these P and Q points converge and there is only one single point, then what we do is that we draw a tangent at that point and we reflect that point. So, that was called the doubling operation. So, therefore, if this P and Q converges at a point say call it say W, then this is nothing but twice of W, because that is W plus W. Okay. So, this is basically that operation of point addition and point doubling. Okay. Now, in elliptic curve cryptography, what we essentially do is that we choose a scalar quantity, say call it lambda, and there is a base point which we call as a point P. Okay. So, the whole point is how do we compute lambda into P. So, that is a basic operation on which elliptic curve cryptography relies, that is how do we compute this value of lambda multiplied by P. So, one obvious way of computing lambda into P is by taking P and by adding it lambda times, right. So, we take P and we keep on adding them lambda number of times. So, what we can do is that we can take a point P and P plus P means it is a doubling operation on P, then whatever output we get again we add that with P and we keep on doing that lambda number of times. So, that is essentially something which is called as the scalar multiplication, which is central to what is known as elliptic curve cryptography. So, whether we want to use it for encryption, whether we want to use it for key exchange, this is the most important and central operation on which elliptic curve cryptography is based on. So, the generic procedure of doing an elliptic curve cryptography is that both parties agree to some public known items. For example, the elliptic curve equation. So, we have studied that the equations of the form of y squared equal to x cube plus ax plus p, that is a possible elliptic curve equation. Similarly, we have got a generalized Weierstrass equation. So, if I give you the values, that is the values of the constants, then you essentially know the corresponding curve equation. Okay. So, it is believed that everybody, the sender and the receiver and even the adversary knows the curve equation. Okay. So, the elliptic, now you have to basically define an elliptic group. Okay. So, the elliptic group computed from the elliptic curve equation and a base point B which is from the elliptic group and similar to something which is called what we have seen as generator used in the context of the previous public key ciphers. Okay. So, similar to that we have got a base point B which is again a public domain information. Okay. So, therefore, these are the public domain information, the values of A and B. Okay. So, what is A and what is B? This is that if you remember the Weierstrass equation, y square equal to x cube plus ax plus p. So, therefore, those two A and B will be important in understanding what is the corresponding curve, right. So, based upon that we have got various varieties of curves, we have got random curves and there are other forms of curves also. Okay. So, and similarly the prime P. So, therefore, the corresponding elements of the elliptic curve are based on some field, right. So, therefore, that field could be a prime field. So, in this case we are assuming that it is a prime field, it could be a characteristic 2 field also like GF2 power of n. Okay. It could be some essentially some complex sets also, but if I assume that for our purpose, let us assume that the underlying elements on the elliptic curve are chosen from Fp, that is it is chosen from the field which is generated out of numbers from 0 to p minus 1 where p is a prime number. Okay. So, the elements on the curves are actually chosen from 0 to p minus 1. Okay. And I mean although I did not say explicitly, all the number of points which are actually there on the elliptic curves, they are actually finite. So, that is basically a finite set of points which are there on the elliptic curve. Okay. So, therefore, you have got your Fp, which is your set of numbers from 0 to p minus 1, where p is a prime number, and then you have got some points which you are actually choosing on the elliptic curve. So, those are actually ordered pairs like Cartesian points x comma y, where x also belongs to Fp, y also belongs to Fp. Okay. So, basically it is a subset of the numbers from Zp cross Zp, right. So, it is again it is a finite set. Okay. So, it is a finite set of numbers and a finite set of points which actually are there on the actual elliptic curve. Okay. And by our previous construction of the addition and the definition of the addition operation on the points, those elements x comma y actually form a mathematical group, right. Along with the point at infinity, they form a mathematical group. Okay. So, therefore, if I take all these points x comma y which actually satisfy this Weierstrass equation, those points along with the point at infinity form what is called a mathematical group, okay, under the definition of the addition and the doubling operation, right. So, therefore, in this case what we are saying is that the public known data items are the values of a, b and the corresponding prime p. These are public known values. Okay. And similarly, there is a base point which is also a public domain value. Now, each user generates their public or private key pair. Okay. So, what is a private key pair here? So, it could be an integer x which is selected from the interval from 1 to p minus 1. So, from 1 to p minus 1, the private key is any integer x which is selected at random, okay. And the public key is actually the product of x and p, b. Okay. So, therefore, what you do is that first of all if you want to use it, right, you first of all choose a corresponding curve equation. So, y equal to x cube plus ax plus b, and whenever you are doing it, there is a modulo p, right, because these elements x and y are essentially chosen from Zp cross Zp. Okay. And these things, that is your the corresponding private key which you are choosing is another number. So, although it is x, but it is a different x actually, it is a secret x. Okay. So, that is x which is chosen from the set closed interval from 1 to p minus 1. Okay. And your public key is actually x multiplied by the base. Okay. So, b is again another public parameter which is the base point of the curve. So, that is generally provided by a central body. So, for example, we have got NIST curves. So, therefore, they essentially gives you these values of a, b and so I think it is better to make it this a and small b. So, this a, this small b and small a and this b is generally provided by a central body, okay, which are chosen curves. So, then this is the way how you choose or calculate this private key and the public key. Okay. So, immediately you know that from our previous discussions, if this x number is chosen from 1 to p minus 1 and this public key value is public, right. So, therefore, everybody knows this x into p. So, therefore, whenever you are using it for cryptography, it is therefore obvious that one should not be able to know this private key, right. So, therefore, it becomes immediate that from this x b it should be difficult to get a knowledge of x, right. That is a basic assumption. So, how do you get x into b? That is by adding b x times, right. So, the repeated additions will give you x into b, and this problem of getting x from x b is what is the basic assumption. Okay. Again, the central believed to be mathematically difficult problem on which elliptic curve cryptography relies upon. Okay. So, anyway, I will come to that in more details. So, at least first of all see that how do we do the basic encryption operation. Okay. Suppose Alice wants to send to Bob an encrypted message. So, both agree on a base point b. So, Alice and Bob creates a public private key. So, what Alice does is that it chooses a private key a and the corresponding public key is p a, which is a b, that is b being added a number of times. Similarly, Bob's private key is again small b and the corresponding public key is b multiplied by big B. Okay. So, now you know that these public keys are actually available to everybody, right, it is there in the public key ring. So, if Alice wants to essentially encrypt a message m, then it has to somehow convert this message or encode this message into a point onto the curve, say call it Pm, right. So, therefore, the first thing is that let us we can actually assume that okay, it's taking this m, somebody can encode that into the point on the curve. Okay. So, therefore, obviously one may ask that how do we essentially take this message m and encode them into the point Pm. Okay. So, there are various ways how you can do so, but one very simple technique is shown here. So, you consider this curve y square equal to x cube plus ax plus b. Okay. So, the plain, so one way could be like this, that is the plain text as say numbers and English or Roman characters whatever you say from 0 to 9 and from 10 to 35. Okay. So, suppose therefore, if I want to send this character b, then this b will be encoded as the number m equal to 11. Okay. So, this is a very simple way of doing so. You see that you choose a public variable say k equal to 20. Okay. And you start computing x which is equal to m into k plus I, and you vary I from 1 to k minus 1. Okay. So, therefore, what I am doing is this, that is you choose this, you know that this value, that is k, is a public known value and you want to send the value m. Okay. So, what you are doing is like this, that is I want to send the corresponding value of m equal to 11, that is what the character b indicates or is encoded as. Okay. So, I want to send this value m equal to 11. So, what I do is that I start computing x, and I start computing x as m multiplied by a publicly known value, say call it 20, and I start adding some value I to it. Okay. And I will vary this I from 1 to k minus 1. So, k minus 1, k being equal to 20 is 19. Okay. I keep on varying this I at one step. Okay. So, for example, in this case it is 11 into 20 plus 1 to begin with when I is equal to 1. So, first of all, in the first iteration I is 1. Okay. So, you get a corresponding value of x, right. So, remember that you are always doing a modulo p, right. So, there is some p through which you are doing, on which you are doing a modulo p operation. Okay. So, let it be some value essentially. So, now if you get this value of x and you know that there is a corresponding curve equation. So, y square equal to x cube plus ax plus b, you take this x and you substitute that into the y, and you know that this is again a modulo p. So, therefore, that means that this number which you get should be a quadratic residue, because if it is so, then there is an integral solution for y. Okay. So, that you can check by our techniques that we have seen previously. You know how to check whether a given value is a quadratic residue modulo p or not, right. So, therefore, you can check whether it is a quadratic residue modulo p. If it is so, then x comma y is a corresponding encoding. Okay. Otherwise, you again start incrementing this I to the next value 2. Okay. And now you know that it is quite easy, you can check that if I start varying from 1 to 19, at least one of them will ensure that y is a quadratic residue. So, if I keep on increasing this like this, then at least one of them will be ensuring that it is a quadratic residue. Okay. So, that you can just think upon why it is so. Okay. So, therefore, m is encoded as x comma y, and the decoding is very simple. The decoding is you take this x, you subtract 1 from it, divide it by k, and take the floor of this value. So, that is your m. Okay. So, you know that x minus 1 divided by k, and you take a floor of this will give you m. So, therefore, this is the way how you can get this value of m from this pair of x comma y. Okay. So, I will give an example on this, that is, suppose p is 751 and a is minus 1, b is 188 and k is 20. So, let this be some arbitrarily chosen values, and your m is again 11. Okay. And I choose this x as x is equal to m into k plus 1. Okay. So, therefore, here if I take this value m being 11 and k being 20, if you multiply 11 into 20 and add 1, you get 222. Is it correct? I think there is a mistake, right? It is 20 into 11 plus 1, okay, this one. So, that is 221, right. Is it 221? it is 221, right. So, therefore, this is please correct it, this is 221. Okay. So, this is 221, but correspondingly we can see that there is no solution for y. So, if you take this value of x and plug into the curve equation, then you will not get an integral value of y. So, that you can check again, but this we can this you can check offline. Okay. So, similarly, so we continue like this and you keep on incrementing the value of this 1, 2, 3 and so on, and you will find in this case that when this I is equal to 4, then your x being equal to 224, and then you will get that there is a corresponding value y equal to 248, which is an integral solution. So, that means that this m equal to 11 can be encoded as 224 comma 248. Okay. So, now I want to obtain back the value of m from this. So, what I do is that I take this 224, subtract out a 1 and divide it by 20, and then take the seal of this, then that is equal to 11. Okay. So, that is essentially how you get back m from the pair x comma y. Okay. So, now I think this should be okay, clear to us, that is why there will be at least one value for which this y is, for which this pair is a valid pair. Okay. So, I am leaving that to you to think, but this is a very simple encoding technique. There could be other principles or other methods through which you can do the encoding also. Okay. So, what is the probability that you will get at least one such thing? If you try, keep on trying, it will be so on that you have to try k number of times, and at least one of them will be a possible encoding. That means the probability is 1 by k, right. That is, so therefore, if you repeat this k number of times, you should get one solution. And the decoding is simple, right. Decoding is exactly gives you back the starting message m. Okay. So, therefore, once we have solved this, that is, once we have done and obtained this value of Pm. So, this Pm is the encoded thing, that is, we have taken the message m, encoded it into onto the elliptic curves, it becomes Pm. Okay. So, Pm is again a point, that is, it is a pair of x comma y, right. It is an x comma y, it is a Cartesian point. Okay. So, now I want to apply and generate the ciphertext. So, what I do in order to generate the ciphertext, I have to use what? I have to use the public key, right. So, what I do, or rather what Alice does is that it chooses a random integer k from the integer 1 to p minus 1. Okay. So, therefore, it chooses the random integer from 1 to p minus 1, call it k, and multiplies it by whose public key? By Bob's public key. Okay. So, therefore, it takes Bob's public key as Pb and multiplies it with k. Okay. So, it multiplies k with Pb and adds it with Pm. So, note that all these additions are defined on the curve. Okay. So, therefore, you choose this, and the other pair is k into b. So, therefore, you already had the base point b, you multiply it scalarly by the corresponding k which you have chosen, and you are passing this pair as a ciphertext. So, this remembers us of the Elgamal encryption, right, on which what we have seen previously. This is exactly similar to that. Therefore, it is called an elliptic curve crypto system, which is analogous to the Elgamal crypto system. Okay. So, you choose Pm and you, so therefore, you add it to k into Pb. So, Pb was your public key of Bob, you have multiplied with k and you have passed it. So, now you can note that in this particular exponent, if you want to obtain Pm from this Pm plus k into Pb, then what do you need to obtain? So, the ciphertext has got Pm plus k into Pb, right, and what is this? This is equal to Pm plus k into the secret, right. So, the secret is b and multiplied by the base point b. So, what was the other corresponding component there? The other component was k b, right. So, when Bob receives it, Bob receives the ciphertexts and Bob has b, right. Bob has b because b is what? B is the corresponding private key, right. So, what Bob does is that Bob takes the first component kb and multiplies kb with the corresponding value of b. So, if you do so, that is, if you multiply this kb with b, then what you obtain is nothing but k into b, and that is nothing but k into Pb, right. So, therefore, Bob by using its own private key can actually obtain the value of k into Pb, and after that it is simple because you have to just subtract out this value and in order to that, so that you get the value of Pm. Okay. So, that is what is shown here, that is if you want to do the decryption, then you take this B and you apply it over Kb, and then you just do this subtraction operation to eliminate these two terms and to obtain back the value of Pm. So, Pm is what? Pm is the encoded message on the elliptic curve. Then again by using the previous decryption or the decoding algorithm rather, you can actually obtain back the corresponding value of M, the message, right. So, this is quite analogous to what we have seen. So, Bob then decodes Pm to get the message M. So, therefore, you have to do the final decoding to get back the original message, right. So, that is how you are actually doing the operation of encryption and decryption. Okay. So, now, so we can obviously extend it for signatures or authentication. So, that I am not actually going into, and that is quite straightforward. Rather, the other interesting application of elliptic curves is in the Diffie-Hellman key exchange. Okay. So, if you just recap, that is what we have seen in context to the finite field P, that is there is a value alpha, you choose alpha power of x a modulo q and obtain y a and send this y a to the corresponding user B, right. So, what the user B does is that the user B obtains computes a y b by again choosing alpha and raising it to some secret value, call it x b, and sending it back to the user A. So, what both user A and user B does subsequently is that uses its own secret value and raises y b to that power, and the other what B does is that it takes y a which it has obtained from user A and raises it to x b, and what we know is that this value of the output value is same, right. So, therefore, that is a final shared or exchanged key, right, which is used for subsequent encryptions. So, we see that the same thing can be done in elliptic curves also. So, elliptic curve and base point so therefore, these are actually the points on the curve. So, what you want is that you want to generate AXY and BXY, and then you want to do some operation on this and similar operation on this, and the expectation is that the output should be the same, right, because and that follows from the elliptic curve definition, right. So, you take B x comma y which Alice has received, but Alice uses its own private key A or randomly chosen value A and computes A B x y, and similarly Bob computes B A x y, and since A B and B are same, that is they are commutative operations, you actually get again another shared key. Okay. So, details is like this, that is you get a private, you choose a private key A, for example, Alice has a private key A and a public key as P A, and similarly Bob has a private key B and a public key as P B. Okay. So, what Alice does is that Alice obtains this corresponding value of B into big B, okay, and multiplies it with its own private key as A. So, that is A into B into big B, and that is same as what Bob computes, because what Bob computes is that Bob obtains A into B from Alice, and then what it does is that it raises it or multiplies it with B, and since A into B is same as B into A, both these two values are same, right. So, therefore, this is the final shared key of A into B into B, big B. Okay. So, that is basically that you can also apply elliptic curves to perform the original Diffie-Hellman exchange as well. Okay. This is simple, right. So, this is same what we have seen previously. So, now why do we use ECCs? Okay. So, in order to understand that, we have to understand that how do we analyze crypto systems. So, obviously, that if I want to say that whether RSA is better than ECC, then we have to compare the difficulties of their underlying problems. Okay. So, for example, RSA is based upon the integer factorization, your Diffie-Hellman is based on some problems which is discrete, is actually based on the Diffie-Hellman assumption. Okay. And similarly, if you want to see the Elgamal crypto system, that is based on your discrete logarithm problem. Okay. And elliptic curve cryptography is again based on the elliptic curve discrete logarithm problem. So, therefore, how do we measure their difficulties? So, we examine the algorithms which are used to solve these problems. Okay. See, for example, here are some values which shows that elliptic curve crypto system results in shorter key sizes. So, therefore, if you compare, for example, here like 163 bits, you will see that a 1024 bit RSA key size is equivalent to that of a 163 bit elliptic curve key size. So, therefore, here you see that there is a significant shortening of the key size. The key size is significantly short, is almost 1:6 ratio. Okay. And as you are going down, the ratio is actually increasing. Okay. So, which means that if you want to apply or rather develop public key crypto systems on resource constrained environments, then elliptic curve is actually a more promising public key cipher. Okay. So, therefore, you will find that if the devices are small, they have limited storage and they have computational power restrictions, then actually elliptic curve cryptography is ideal. Okay. And that is why it is actually trying to probably, I mean, it is being adopted worldwide. Okay. So, therefore, if you want to apply for wireless communications, for smart cards, develop online transactions, web servers, that is any application where security is needed, but also I mean the place or the platform lacks sufficient power, storage and computational requirements. So, therefore, this is very very motivating and very useful for the present day applications. Okay. So, therefore, the difficulty of the so the question is why essentially RSA has got such a bigger key size and elliptic curve cryptography has a comparatively much smaller key size. Okay. So, that in order to answer this, it has got to do with the underlying hardness of the problem, that is what is the corresponding difficulty of solving the inherent internal problem, that is how hard is it to solve the Diffie-Hellman problem in elliptic curves and how hard it is to solve the Diffie-Hellman problems in FP. Okay. So, that is the basic question. So, your elliptic curve security. Okay. So, therefore, the question is that the hard problem is analogous to discrete logs, that is q is equal to k into p. So, the question is that there is a point p and there is a point q, and the question is that given k and p, it should be I mean easy to compute q, but it is should be hard to find the value of small k, that is the scalar. So, that is this problem is known as the elliptic curve discrete logarithm problem. Okay. So, in this case we know that k must be large enough, that is if k is small, say 1 or 2, obviously it is not difficult, but it becomes difficult when is k is really large, right. So, elliptic curve security relies on elliptic curve logarithm problem and it can be compared to other problems that we know of. So, this is the basic definition of elliptic curve discrete logarithm problem more formally. So, let E be an elliptic curve over the finite field f p, okay, and let p and q be points in this E f p. Okay. So, therefore, there is an elliptic curve and there are two chosen points p and q, and we are actually interested in the elliptic curve discrete logarithm problem. Okay. So, therefore, the elliptic curve discrete logarithm problem is the problem of finding an integer n such that q equal to n p is satisfied, that is given this value of p and given this value of q, how hard it is to compute this value of integer n. Okay. So, we denote this integer n as n is equal to log q base p. Okay. So, that is the elliptic curve discrete logarithm of q with respect to p. Okay, that is the elliptic curve, I mean this is the elliptic curve discrete logarithm of q with respect to p. So, now we will see certain interesting properties of this elliptic curve discrete logarithm problem. Okay. So, one of the things is that this log q base p may not be defined. Okay. That is, you may choose 2 points q and p such that this log q base p is actually not defined. Okay. Why? Because it is not necessary that always you will find that q and p maintains a relation, that is q is equal to n into p. Okay. So, it may be that there are 2 points for which q is never equal to n into p for any integer n. Okay. So, that is actually something which is to be kept in mind, but the thing is that we actually are not really faced with any problem because of this fact, because of the nature in which how we are actually applying our elliptic curve cryptography, because whenever we are applying elliptic curve cryptography is by repeated additions, right. So, then the corresponding q and p that we are generating or that we are concerned of actually has got this relation, okay, but it is not true for any arbitrarily chosen q and p values. Okay. So, therefore, since there are so therefore, it is important to be kept in mind, that is, it is not necessary that for any q and p this elliptic curve or this discrete logarithm has to be defined, okay, but the manner or the fashion in which we are applying this elliptic curve, okay, that we do not face any significant problem. Okay. So, now there is the other important thing is that there is not a single value for which this holds, that is, it is not true that this q equal to n p is, that is n into p is true only for one unique value of n. There can be multiple solutions to this equation. Okay. So, why? Let us just try to see this, because this is quite straightforward. That is, suppose you know that you choose any point p, okay, there will exist an s such that s into p will be equal to O. Okay. So, that follows from the basic property that we have that is of the underlying group, that is, if you keep on adding p, then there will exist one such integer s for which s into p is equal to the identity of the group. Okay. And the least such value for which this holds is actually called the order of the point p. Okay. So, now the other fact that also is important is that you know that the points on the elliptic curves are actually finite set of points. So, if you just take any point p and you consider p, 2p, 3p, 4p and so on, you know that there must be two such values I and j for which they are the same, because it is a finite set of points, right. So, therefore, if you choose I, so there must exist some value I, there must exist some value of j, okay, where I is greater than j, say without any loss of generality, for which I into p is equal to j into p. Okay. So, that means, if you rearrange, then I minus j into p is equal to O, right. So, therefore, if you say that s is equal to I minus j and the smallest such s is called the order of p, so then you know that there must exist some case for which this I into p is equal to j into p. Okay. Then, so, therefore, if n 0 is an integer such that q is equal to n 0 p, suppose there is one such value, that is, there is one such value for which n 0, there is one such integer n 0 for which q equal to n 0 p is satisfied. Okay. So, then you can actually choose any n by adding n 0 with I multiplied by s, then this also will satisfy this equation of q equal to n p, right, because you know that q equal to n p is nothing but here n 0 plus I integer the order s, that is the order of the point p, and you are adding p to multiplying it p, right. So, therefore, that is equal to n 0 into p plus I into s p, and what is s p? S p is O, right. So, what you get is back as n 0 p, right, and you know that q equal to n 0 p is satisfied. So, therefore, this actually holds. So, therefore, this logarithm is actually, when you are considering this logarithm of the point q with the respect of point p and you are obtaining a corresponding integer value, is actually a mapping, right, mapping from what to what? Mapping from 2 points, right, q is a point, p is a point, right. So, there are 2 points on the curve, say I call it a point p 1 and point p 2, there are 2 points on the curve to an integer n, okay, and this integer you can actually denote as z, and you can actually choose it as sz, because you know that any such thing will satisfy, that is, any n 0 plus I into s will satisfy, but we are actually interested in the least representative of this class, right, and therefore, what we choose as the least difference of the class is either by this or, so essentially this is my the minimum set, right. So, therefore, I can actually choose, so I can actually obtain various classes, and I am interested in this congruence class. Okay. So, therefore, that is the way how we choose this corresponding thing. Okay. So, therefore, we are interested in the least such value. Okay. So, we are interested in actually yeah, sorry, I mean this is probably a more customary thing, right, Z S Z, right. So, do you understand this? That is, essentially there can be more than one solutions to this discrete log problem, but what we are interested in is a least such value. Okay. So, therefore, if we know that the order of the point P is S, we can actually take any value which satisfies this, and we can actually obtain the corresponding modulus with respect to S, right. That also will should satisfy this equation, right. So, how many solutions are there? There are large number of solutions. You can actually keep on generating solutions like this, right. Now, the question is how hard is the elliptic curve discrete log problem. Okay. See, so we have studied in context to the previous algorithms, like in context to previous RSA, when we have studied L-Gamal crypto systems. We actually did not go much into the cryptanalysis of L-Gamal crypto systems, but there are actually algorithms which are better. For example, if you remember in context to factorization, we have discussed about algorithms which had a complexity of O n to the power of 1 by 4th, because if you want to generate, right, that if you remember that algorithms like Pollard's row algorithm, so they were quite efficient algorithms, right, in order to factorize or rather to find the prime factors of a given composite number. Okay. So, that if that problem is solved, then the RSA problem is also solved, right. So, therefore, now the question is how hard is the elliptic curve discrete logarithm problem. Okay. See, for example, just so if you remember the birthday paradox, consider as approach which is similar to the birthday paradox. Okay. So, we know that if I generate two lists L1 and L2 based upon say r random choices of values like J1 to Jr and K1 to Kr. So, what I do is that I just generate J1 to Jr randomly, and all these things are actually from 1 and P. Between 1 and P you choose any arbitrary values. Okay. So, what I do is that I obtain J1 P, J2 P and so on till Jr P. I generate similarly another list which is built upon like K1 into P plus Q, K2 into P plus Q, okay, and then Kr into P plus Q. So, if you find that in these two lists there is a collision, okay, so then you know that J u P, that is for some u, is equal to K v plus P plus Q. So, therefore, you can immediately rearrange, and you know that one solution is J u minus K v. That means, if I get this list and if I get this list and there are two such values for which the common term occurs, then you can actually solve the elliptic curve discrete log problem, right. Now, how difficult, or rather what should be the least value of this value of r for which you get a collision. So, you can actually you know that these values being from 1 to P, there are P such values, and if you apply the birthday paradox, if you set your r to be of the order of P to the power of half or square root of P, you know that you have got a very good chance or very high probability of finding a collision, right. That is the customary birthday paradox approach. So, therefore, you know that if r is of the order of P power of half, then you can actually obtain an elliptic curve discrete log solution. Okay. And the interesting thing is that this is probably the kind of fastest algorithm that has been yet been found to solve the elliptic curve discrete log problem, which has got a complexity of O P power of half. Okay. So, there are algorithms of the nature of something which is called as index calculus algorithms, which actually are having an order of so solving, the runtime is of the order of P power of half. But whereas for the previous things like for the discrete log problem in FP, there are much more advanced and much more faster algorithms, right. So, if you remember that what was it, you can actually quite easily find out whether not easily rather, but you can find out if you want to factorize a large composite number, and if you apply a Pollard's row kind of algorithm, then you remember that the complexity of that was, if the factor of that is, if n is can be factored as P into Q, then the complexity of that was O P power of P root P. So, and P is of the order of root n. So, therefore, the complexity was n to the power of 1 by 4, right. So, that was a faster kind of algorithm, right. So, similarly, but in the context of elliptic curve discrete log problem, there has the fastest algorithm which has been found to solve this elliptic curve discrete log problem is of the order of P power of half. Okay. and there are actually developments of course in the context of elliptic curve discrete log problem by bringing in the concepts of pairings. Okay. So, first of all, pairings in cryptography were first actually used to solve the elliptic curve discrete log problem, that is they were used in that sense in a cryptanalytic sense, but after that it was actually used in a positive sense in developing ciphers. But the first use or usage of pairings was in the cryptanalysis of elliptic curve discrete log problems, right. So, therefore, the general comment that we can make is that the elliptic curve discrete log problem is probably harder than the discrete log problem in FP star, okay. And the discrete log problem has actually, I mean FP has actually got faster algorithms. That means, we can actually do in elliptic curve discrete log problems with a shorter key size, that is the reason why we can actually do away with shorter key sizes. Okay. So, I can give you one question here, that is which you can take and think upon, is that suppose there is p which is greater than 3, which is an odd prime, and a and b both belong to ZP. Okay. So, further suppose that the equation of this will be x cube. Okay. So, it is x cube plus ax plus b equal to 0 modulo p has got 3 distinct roots in ZP. Okay. So, one question is that prove that a corresponding group, that is G equal to E plus, is actually not a cyclic group. Okay. So, that is it is not a cyclic group. So, therefore, you remember the definition of cyclic group, that is in this case you can actually take any generator and you can repeatedly apply the addition operation on that, and you should be able to construct the entire group. Okay. So, therefore, the corresponding curve corresponding or the corresponding group is G equal to E plus, where E is defined as y square equal to x cube plus ax plus b, and you are doing a modulo p operation. Okay. So, the question is that you have to prove that a corresponding group here is actually not a cyclic group. Okay. So, we have given you some hints here. So, the first thing is that to prove that if you take a point p 1, say call it alpha 1 comma 0, this has actually an order of 2. So, order of 2 means what? Yeah. So, that means that if I take p 1 and if I add p 1 with p 1, I should get O, right. So, this is the first exercise which you can take, that if I take p 1 and if I add p 1 with it, then I get back O. So, for that you can, it is very simple, you can see that you can, if I want to obtain the doubling operation here, then I have to take a differentiation of this. You can actually, there is a small catch here, that is you cannot apply the doubling equation straightforward, because in the doubling, if you remember in the derivation we had assumed that y was not equal to 0, but here your y is equal to 0 of this point. So, if I take a differentiation here 2y dy dx, you know that it is 2y dy dx 3x square plus a, that is a point, right. So, therefore, the dy by dx at the point of say alpha 1 comma 0 is not defined, because you are actually dividing by 2y. So, that is a vertical line. So, therefore, the vertical line will intersect the elliptic curve at the point O. So, therefore, 2 into p 1 is actually equal to O. So, that is why its order is 2. Okay. So, similarly, you can actually generate points like p 2 which is alpha 2 comma 0 and p 3 as alpha 3 comma 0, all of them have got order of 2, right. So, now if this alpha 1, alpha 2 and alpha 3 are distinct roots of these 3 equations, okay, or this equation, then you know that alpha 1 plus alpha 2 plus alpha 3 is actually equal to what? From theory of equations, it is equal to 0, because there is no term which is an x squared term, right. So, therefore, alpha 1 plus alpha 2 plus alpha 3 is equal to 0. Okay. So, using this you can actually show that this p 1, p 2 and p 3 along with the point at infinity O actually forms a group, that is it forms a subgroup. Okay. And the other point to be noted here is that this subgroup, that is consisting of p 1, p 2, p 3 and O. So, subgroup means first of all you have to define that it is an closed set, that is what you have to show. The other thing is that this subgroup is actually not a cyclic subgroup. Okay. That is, there is no generator which will generate all of them, and that is quite simple to check. and if the subgroup is not cyclic, then the group is also not cyclic. Okay. So, this is actually a problem from Stinson. Okay. So, therefore, this is a sketch of the solution which you can complete. Okay. So, these are some of the references, along with I have also used the standard Douglas Stinson's book also as a reference. Okay. So, next day's topic will be implementation of elliptic curve cryptography.